Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to describe the determinant. So in this topic, we will describe the concept of a change of area or volume. We will then describe the idea of orientation. We will see that matrices always change the volume by a fixed ratio. This ratio will be called the determinant, together with a sign that describes orientations. We will find the determinant of simple row operation matrices. We will use this to find the determinant of an arbitrary matrix. We'll look at some consequences, and we'll see some simple formulas for calculating the determinants of small matrices. Now, let's start with an observation. If we take a square matrix and find the image of a number of regions, for example, let's take this matrix here, 1, -2, 2, 3. Here I start with the region that is the red square. If I map every single point in that region by this matrix, I get the rectangle or the parallelogram that is in blue. The ratio of those areas, if you were to calculate it, is 7. So the blue parallelogram is 7 times the area of the unit square. For that same matrix, if I take the unit circle with area pi, then the image of the unit circle is this ellipse, and the area of that ellipse is 7. We note that the ratio of the areas always seems to be the same. Now, suppose that we are in R to the n, and we consider the region defined as all vectors where all entries fall on the real interval 0 to 1. So for example, in R1, this is a unit line with length 1. In R2, this is a unit square with area 1. And in R3, this is the unit cube with volume 1. In R to the n, we will refer to this as the unit n cube with an n volume of 1. Also, in R to the n, if we consider all vectors such that their 2 norm is less than or equal to 1, we will describe this as the unit n ball. We can actually calculate the volume based on one of these two formulas, depending on whether or not n is even or odd. Here, n double factorial is n times n minus 2 times n minus 4, going all the way down until we reach either 2 or 1. Now, from these formulas, we deduce that the volume of the 1 ball, or the unit line from -1 to 1, is 2. In R2, this describes the unit circle, which has an area of pi, and in R3, this describes the unit sphere, which has volume 4/3 pi. Now, in general, given a region P in R to the n, you can deduce that it is possible to therefore estimate its n volume. Now, notice that a point in R1 does not have any length. A line or curve in R2 does not have any area, or 0 area, as does a point. A point also has no area. A plane or surface, or a line or a curve in R3 also does not contain any volume. So in general, a subspace that is not all of R to the n will have 0 n volume. Now, suppose you have a region P in R to the n, and that region P has an n volume denoted as the volume of P. Suppose now we multiply every point in that region by a square matrix A that maps Rn to Rn. So the question is there a relationship between the volume of A applied to each point of P and the original volume of that region P? And if so, can we calculate this ratio? Let's simplify this problem. Rather than looking at an arbitrary matrix, let us consider taking the unit n cubed and multiplying every point in that unit n cubed by the matrix R sub alpha times rho k. So this is a row operation that multiplies the kth entry of a vector by the scalar alpha. So in R2, we have two such options. We could, for example, multiply the first entry by 3. Now that's going to increase the area of the unit square by a factor of 3. The alternative is that I can multiply the second entry by a scalar such as 0.5. Well, that's going to change the area by a factor of 0.5. So given an operator A, let us define the determinant of A to be the ratio of the n volume of a region A times P over the n volume of the original region P, assuming it is defined. So in this case, it seems that multiplying the kth entry of a vector by alpha, that row operation has a determinant of alpha. So, for example, multiplying the first entry by 3 seems to have a determinant of 3. It will change every single volume by a factor of 3. Similarly, multiplying the second entry by a half seems that it will have the area of any region. Now consider the following. What happens if alpha is less than 0? Under this definition, multiplying the first entry of the vector by -2, that seems to have a determinant of -2. So the unit square is mapped to this rectangle. So what does it mean to have a negative determinant? Well, let us interpret a negative number as having a flip in orientation. Now, what does that mean? For example, if you take a look at yourself in the mirror and you are holding something in your left hand, when you look at yourself in the mirror, it appears as if it is in the right hand of your image. Incidentally, if you look at yourself in a mirror where you see yourself in a mirror, the object in your left hand once again appears to be in your left hand. All right, how about the effect of swapping two rows in a matrix? If we multiply a vector by this row operation, this has the same effect of swapping two entries in that vector. So here in R2, we see the unit square. If we swap the two rows of a vector, of each vector in that unit square, we get back that unit square. So it seems at least that the operation of swapping two rows seems to preserve the area. So in that case, the absolute value of the determinant of such a matrix is going to be plus or minus 1. However, let's take this region here. If I multiply each point in this region by this matrix, I get this region here. Now, if you look carefully, this is actually a reflection in the line y equals x. And so it's actually going to be a flip in orientation. So basically, the determinant is going to be -1. Perhaps it's easier to see in an image. Here, the square tower is apparently on the left of the image, or left of the building. However, if we multiply every single point in this image by that matrix, we actually get this image here, and here we see that the square tower appears to be on the right. So yes, there does appear to be a flip in the orientation. How about the effect of adding a scalar multiple of one row onto another? So here we are adding twice row 2 onto row 1. In a vector, this has the effect of adding twice the second entry onto the first entry. Well, if we multiply every single point in the unit square, we see that the area hasn't changed. We've simply sheared along the first dimension. So consequently, it seems that adding a multiple of one row onto another, or if we're multiplying a vector by this matrix, adding a multiple of one entry onto another, has the effect of completely preserving the area, and so therefore the determinant is equal to 1. Now, given a single linear operator on r to the n, we have defined the determinant of that operator as the change, or the ratio of the change in n volume under that linear operator. So consequently, we may ask, suppose we have two linear operators, a and b, and we have a region, and we first map every point in that region under the mapping A, and then on that image map every point under the linear operator B. In that case, what is the ratio of the original region to the final region? Well, for example, let us assume we start with the unit square and multiply every single point in that unit square by the 2 by 2 matrix A. We may get this region here. Now, the ratio of those two regions appears to be approximately 2. So the determinant of A would be approximately 2. It could be plus or minus 2, however, because there may be a flip in the orientation. Now, let us assume we have a second linear map B. This linear map is going to take this second region, and if we multiply every point in that second region by B, we get this region here, which once again seems to be approximately twice the area of the second region. So the determinant of B also appears to be approximately plus or minus 2. So what is the change in region from the first, change in area from the first region to the last? Well, it seems that the determinant of B times A is the determinant of B times the determinant of A. And that's also true if, with respect to the orientation. If A flips the orientation, or is negative, and B flips the orientation again, then we're back to normal. So a negative times a negative is a positive. If, however, only one of these linear maps has a negative determinant, then under one mapping, orientation is preserved, under the other, orientation is flipped, and so ultimately under both, the orientation will continue to be flipped. So yes, it does seem that correctly the determinant of a product of two matrices is the product of the determinants, because, after all, if the ratio of n volumes between the first and second regions is one ratio, and the ratio between the second n volume and the third is a second ratio, then the ratio between the first volume and the third will be the product of those two ratios. Now, here's a different operator. Given the identity operator on r to the n, the determinant of the identity operator is always 1. Proof. Well, given any region P, then the identity operator applied to each point in P gives us the exact same region, and so the volume is unchanged. Also, there's no change in orientation as every single point stays in the same location. Consequently, the determinant must be equal to 1. All right, let's take a look at some consequences. Given a linear map on Rn, and given m row operations that add a multiple of one row onto another, and let us assume that if we apply these row operations to A, then the application of these row operations applied to A will give us a new matrix U. If that's the case, then the determinant of A is equal to the determinant of U. Proof. Well, if this product of row operations applied to A gives us the matrix U, then the determinant of the product of matrices equals the determinant of U. Now, the determinant of a product of matrices is equal to the product of the determinants. However, we noticed that the determinant of adding a multiple of one row of a matrix onto another row, that is, adding a multiple of one entry of a vector onto another entry of that vector, each of those has determinant 1. So 1 multiplied by itself m times, multiplied then by the determinant of A, is going to still be equal to the determinant of U. Thus, that proves this theorem. For example, let us start with a 2 by 2 identity matrix that has determinant 1. If, on that matrix, we add 0.5 times row 1 onto row 2, and then, on the result of that, add -3 times row 2 onto row 1, you will notice that all three of those matrices have determinant 1. If we calculate the product of those three matrices, we get the matrix on the right. Consequently, the determinant of the matrix on the right must be also equal to 1, because it is the product of three matrices, each of which has a determinant of 1. Let's check that result. Let's multiply each of the points of the unit square by the matrix that we determined. In this case, we get this parallelogram. If you were to calculate the area of this parallelogram, you would notice that it is equal to 1. Also, you could determine that there was no change in orientation either. Now, here's another theorem. Given A mapping Rn to Rn, and given m plus n row operations, where m of these row operations add a multiple of one row onto another, and n of these swap two rows, And if we apply these m plus n row operations onto the matrix A to get the square matrix U, then the determinant of U is equal to the determinant of A times -1 raised to the power n, where n is the number of row swaps. Proof. From our observation, if U is equal to a product of matrices, then the determinant of that product of matrices is equal to the determinant of U. Thus, the determinant of U is equal to the product of the determinant of these matrices. However, the determinant of each of the row operations we've discussed here is plus or minus 1. Now, m of these row operations have a determinant 1 because adding a multiple of one row onto another has determinant 1. N of these row operations have determinant -1 because they are swapping two rows, and that has the effect of making a reflection which changes or flips the orientation. Consequently, those n matrices have determinant -1. Therefore, the cumulative effect of those n matrices is -1 to the n. That proves our theorem. Theorem. Given a diagonal operator, that is, a diagonal square matrix, then the determinant of that matrix is the product of the diagonal entries. Proof. Well, we can actually write the diagonal matrix D as the product of multiplying the first row of a matrix by the first entry on the diagonal, multiplied by multiplying the second row of the matrix by the second entry of the diagonal matrix, and so on and so forth up until the last entry of the diagonal. Now, the determinant of the diagonal matrix is equal to the determinant of the product of these matrices. And the determinant of a product is the product of the determinant, and the determinant of multiplying a row by a scalar is that scalar. Consequently, we get that the determinant of a diagonal matrix is simply the product of the diagonal entries. For example, let us start with a 2 by 2 identity matrix that has determinant 1. If on that matrix we add 0.5 times row 1 onto row 2, and then on the result of that add -3 times row 2 onto row 1, you will notice that all three of those matrices have determinant 1. If we calculate the product of those three matrices, we get the matrix on the right. Consequently, the determinant of the matrix on the right must be also equal to 1, because it is the product of three matrices, each of which has a determinant of 1. Let's take a look at this result. Here we see an image, and in this image, the tree is to the left of the tower. If we multiply every single pixel in that image by this matrix, we get this image here. Now, you will notice that this image has approximately 50% more area. Well, actually it has exactly 50% more area. But not only that, whereas in the original image the tree was to the left of the tower, in the image the tree is to the right of the tower. Theorem. Given a matrix A that is square, and it is also in row echelon form, then the determinant is the product of the diagonal entries. Proof. Let us begin with the assumption that the rank of the matrix is equal to n. That is, the matrix must therefore be an upper triangular matrix with no zero entries on the diagonal. In this case, let us start with the identity matrix. First of all, perform the row operation of multiplying each row by the non-zero diagonal entry of the matrix A. Again, we're assuming the rank of the matrix is n. Well, in this case, once you have performed those n operations, you can then carry on by adding appropriate scalar multiples of subsequent rows onto previous rows to fill in the upper triangular portion of the matrix to finally get back to the matrix A. Well, consequently, the first n row operations had a determinant equal to the corresponding diagonal entry, and all of the other row operations, that of adding a scalar multiple of one row added onto another, each has determinant 1, and therefore the overall determinant is simply the product of the diagonal entries. Note, however, if the rank of A is less than n, then to get from the identity matrix to the matrix in row echelon form, it will be necessary to multiply a row by 0. Hence, no matter how many row operations we have, be they row swaps, adding a multiple of one row onto another, or multiplying a row by a scalar, the product of all of those will be dominated by the fact that one of those row operations was multiplying a row by 0. That has determinant 0, and therefore 0 times anything else is still going to be equal to 0. Thus, to multiply a row by a 0 is a non-invertible operation. If I multiply a row by 0, I can't get back. There is no inverse. And thus this is further evidence that if the rank of a matrix is less than n, the matrix is not invertible. That is, you can't get back to the identity matrix from another matrix if, to get to that matrix, you had to multiply a row by 0. Now here's another nice argument. If the rank of A is less than n, then we can also see that the determinant is 0 because the image of any region will be a subspace of the range. But the range will not be all of R to the n. Consequently, we saw or argued previously that, for example, in R3, a plane has no volume. Neither does a line, neither does a point. Consequently, a subspace that is not all of R to the n has 0 n volume. Therefore, any subset of something that has 0 volume must still have 0 volume, and therefore the image of any region under a mapping A that has rank less than n must therefore also have 0 volume. Thus, the determinant should be 0. Now, given a matrix A mapping Rn to Rn, to find the determinant, simply convert the matrix to row echelon form, and during this process, record the number of times N that row swaps were performed. Then, if U is the row equivalent matrix that is in row echelon form, then the determinant of A is equal to -1 raised to the power N times the product of the diagonal entries of the matrix that is in row echelon form. Sketch of the proof. Well, to get from the matrix A to the matrix that is in row echelon form, all we did was apply row operations of swapping two rows and adding a multiple of one row onto another. The first, swapping two rows, has a determinant of -1 each. Each of the second ones, adding a multiple of one row onto another, has a determinant of 1. Because the determinant of a matrix that is in row echelon form is the product of the diagonal entries of that matrix, it therefore follows that the determinant of A is equal to -1 raised to the power of the number of row swaps that occurred times the determinant of the matrix in row echelon form. And the determinant of the matrix in row echelon form is the product of the diagonal entries of that matrix. Theorem. A matrix A mapping Rn to Rn is invertible if and only if the determinant is non-zero. Well, a matrix is invertible if and only if the rank of A is equal to n, which is true if and only if all diagonal entries of the row equivalent matrix that is in row echelon form are non-zero, which is true if and only if the product of the diagonal entries is non-zero. And therefore, that is going to be either plus or minus the determinant of A. Theorem. If a matrix A is invertible, then the determinant of the inverse of the matrix is equal to the reciprocal of the determinant. Proof. If A is invertible, then A times its inverse is equal to the identity matrix. Thus, the product of the determinants of A and the inverse of A is equal to the determinant of A times A inverse, which is equal to the determinant of the identity matrix, which is equal to 1. Therefore, dividing both sides by the determinant of A, we get that the determinant of the inverse of a matrix A is equal to the reciprocal of the determinant of A. Yet again, another proof that the determinant of a non-invertible matrix is 0. Theorem. If both A and B are matrices mapping Rn to Rn, the matrix BA is invertible if and only if both A and B are invertible. Proof. Well, the determinant of B times A is equal to the determinant of B times the determinant of A. And the determinant of the product of the determinants is going to be non-zero if and only if both the determinant of A and the determinant of B are non-zero. There are two special cases where it is easier to calculate the determinant than converting the matrix into row echelon form. First, the determinant can be calculated for a 2x2 matrix as multiplying the two diagonal entries and subtracting the product of the off-diagonal entries. So the determinant of the matrix ABCD is AD minus BC. That's the same as multiplying those two entries together and subtracting off the product of those two entries. Now, the determinant of this matrix that is 3 by 3 is given by the following formula. We are not deriving this formula. However, you can get this very easily by writing down the entire 3 by 3 matrix twice and then calculating the product of these diagonals. So A times E times I plus B times F times G plus C times D times H. From this, subtract off the product of these three diagonals. A times F times H minus B times D times I minus C times E times G. Now, something that's very critical. This pattern does not work for R4 or higher. Do not try to find a shortcut in calculating the determinant for a higher order matrix other than one that is 3 by 3. All right, now while we have argued that a matrix is invertible if and only if the determinant is non-zero, do not ever use this test for invertibility. Numerical error means that it's almost guaranteed that the determinant will never be 0. It will almost certainly be a non-zero value even if the determinant is 0. For example, this matrix here is not invertible. The determinant is equal to 0. However, if I ask MATLAB to calculate this determinant, I get 6.666 times 10 to the negative 16. That's a very small number, but it is non-zero. Now, the problem is that a small determinant does not mean that the matrix is not perfectly invertible. For example, the determinant of this matrix is 10 to the negative 18, which is much smaller than the previous one. However, the inverse exists, and it's really easy to calculate. It's just 1 million on the diagonal entry. So following this topic, you now understand the idea of n volume in R to the n. You understand that row operation matrices change these n volumes with simple to calculate formulas. You understand the idea of the determinant and the idea of orientation and how a matrix can flip an orientation. You know that the determinant of a product of matrices is the product of the determinants. You know how to find the determinant of an upper triangular matrix, and that of course includes those matrices that are in row echelon form. You know how to calculate the determinant of an arbitrary matrix, and you know how to calculate the simple formulas for finding the determinants of 2 by 2 and 3 by 3 matrices. Now, one final warning. Some of you will search online to find how to calculate the determinant. You will come across formulas described as cofactor expansions with lots of tricks to speed up this absolutely horrible algorithm. Associated with this are the classical adjoints for calculating the inverse. We will cover none of these in this course, and we shouldn't. These formulas have worse runtimes than almost all other algorithms you will see here at the university and probably throughout your life. They are highly susceptible to numerical error. For calculating the determinant of a 10 by 10 matrix, using these algorithms requires about 3 million floating point operations. For the same problem, Gaussian elimination requires, a few thousand. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!